Why bins plug? The 3 root causes of bin plugging. Kamengo was born out of a research team that spent 15 years looking at the question of why bins plug. Why is it that when you put material into a storage bin, nothing comes out? Or nothing comes out, and then everything comes out? The first half of the team's research focused on bin design, the second half focused on the feeder. In response to the question of why bins plug, the research team identified 3 root causes of bin plugging and uneven discharge. The first, poor bin geometry, is pretty intuitive. The standard that Kamengo uses is that if the feeder were removed from your storage bin, the bin should self-empty with only the aid of gravity. If it doesn't, there is something wrong with the geometry of the bin. And I'm going to talk a bit more about what I mean by correct bin geometry. The other 2 root causes, compaction by the feeder and uneven discharge, they're a bit more counterintuitive. This is because they have to do with the behavior of the feeder creating problems up above in the storage bin. And what makes them counterintuitive is that it's not visually apparent that the behavior of the feeder is a culprit of poor discharge. To dive deeper into these root causes, to better understand their implications and how to resolve them, I want to take us back to the 1970s and the original work undertaken by the Kamengo team. The starting point for the Kamengo team's research was the early work done by Dr. Andrew Jenike at the University of Utah in the 50s and 60s. Jenike developed the theory for translating a bulk material's flow properties into a bin design that can self-empty with gravity. The Kamengo team was interested in testing the limits of Jenike's theory, so they built themselves a full-size bin where they could adjust the angles of the bin wall, change the length and width of the discharge opening, and change the bin wall liners. And in the beginning, there was no feeder. Instead, the bottom of the bin was held with plywood. The team would set the bin up according to the results of the testing, fill the bin up, and then pull the plywood and observe whether the material would discharge or not. And through systematic testing of a variety of cohesive and large particle bulk materials, they showed that yes, Jenike's theories very much apply to a wide range of difficult flowing bulk solids and can reliably predict the minimum geometry required to discharge a bulk solid with only gravity. In broad terms, Jenike's theory reduces bin design to a physics problem. On the one hand, you have gravity, which is fixed and limited, and this is the primary force available to discharge a storage bin. And on the other hand, you have the forces working against gravity, including the strength of the material. And good bin design is about making sure you're asking less from gravity than what it can provide to empty the bin. I want to give you a quick primer on the contents of Jenike's theory. Essentially, Jenike's theory centers on making key decisions on the geometry of the storage bin, but the starting point is the desired flow pattern. And what I mean by that is how material flows and moves in the storage bin or pile. So there are 2 flow patterns to choose from. You have mass flow, where material discharges in a first in, first out flow pattern. Here, the stored material moves down the bin as a single mass. All of the material in the storage bin is in motion. The alternative to mass flow is funnel flow. funnel flow is a first in, last out flow pattern. Here, material shears through the center of the bin from the top down. Now, to get mass flow, you need to design for it. In simple terms, for a given wall material, be it mild steel, stainless steel, or a fancy liner, there is a minimum slope required to achieve mass flow. If the angle of the sloping walls of the bin is shallower than this angle, then you get funnel flow. Now, there are two basic rules that I want you to remember. If you are designing for mass flow, the discharge outlet of the storage bin needs to be greater than the bulk solid's bridging dimension, which is a minimum diameter or a minimum width and length, depending on whether you have a circular discharge opening or a rectangular discharge opening. If the outlet is not greater than the bridging dimension, the storage bin is at risk of suffering from chronic bridging over the feeder. Alternatively, if you are designing for funnel flow, the discharge outlet of the storage bin needs to be greater than the bulk solid's piping dimension. Otherwise, the bin will be susceptible to rat holing, which is a particularly dangerous form of plugging. All of these dimensions, minimum angle, bridging dimension, piping dimension, they are all determined through material flow characterization testing, which is a series of bench scale laboratory tests developed by Dr. Jenike. Now, something to keep in mind. The piping dimension is often 2 to 10 times larger than the bridging dimension. And for particularly nasty bulk solids, the piping dimension can be so big that it is unreasonable to make work in a storage bin. In these cases, you need to design for mass flow. Now, going back to the Kamengo team and their research, they were able to demonstrate that using Jenike's theory, we can derive a bin geometry for a bulk solid that will result in a storage bin that can self-empty with gravity. But that's not enough. You need to be able to meter material from your bin or pile. For the Kamengo team, they tried a belt feeder, a screw feeder, and an apron feeder with their test bin to meter material from their bin. But what resulted surprised them, because here was a bin that they knew would self-empty with gravity. I mean, they had seen it self-empty with gravity. But in each case, as soon as they added the feeder, it started experiencing severe plugging. The question is why? The team found their answer by observing the feeder's effect on the flow pattern inside the bin. Their first observation was that the feeders were doing two things at once. They were trying to meter material while conveying material to a single point. And it is the conveying action of the feeder, which is shearing material from the bin, that was resulting in compaction. You can imagine that with a cohesive bulk solid, the material you are shearing out of the bin is carrying material above it, either through interlocking or friction, and driving this material forward, and ultimately compacting this material against the bin wall. This compaction can have severe consequences. With many bulk solids, when you compact them, they gain strength quickly. And the more shear strength a bulk solid has, the wider the opening it can bridge over. Compact a material enough and it will bridge over your feeder. So that was their first problem. Their second observation was that the feeders were pulling material preferentially from one area of the bin, usually the rear of the bin, leaving a stagnant pocket of material most often at the front of the bin. The problem here is that when it comes to avoiding bridging or piping in your storage bin, ultimately, it's not the dimensions of the bin discharge outlet that matters, What matters is the effective discharge area, which is the area that the feeder is withdrawing from. In other words, regardless of the physical width and length of your bin discharge outlet, if the area that the feeder is pulling from does not overcome the bridging dimension or the piping dimension, you get bridging or piping in the bin. Now, the selective withdrawal of material by the feeder raised a second, more severe consequence. You see, the test bin was set up for mass flow because the team was working with materials that would not easily funnel flow. What the researchers found is that despite the bin geometry being set up for mass flow, with the unbalanced withdrawal of material, they were not getting mass flow. Instead, they were getting funnel flow. Remember the definition of mass flow. All of the material in the storage bin is in motion. It all comes down as a single mass. Effectively, the behavior of the feeder had turned their mass flow bin into a funnel flow bin. And because the discharge opening of the bin was designed to overcome the much smaller bridging dimension and not the much bigger piping dimension, the result is that they should expect piping or rat holing in the bin. For the Kamengo team, observing the behavior of the belt, screw, and apron feeders got them thinking, can they rethink the feeder? Instead of having a feeder that withdraws material preferentially from one part of the bin, can we have a feeder that withdraws material evenly from its entire opening? And can we avoid the compaction that results from shearing material from the bin, which injects strength into the stored material? If we know that we can design a bin that can self-empty with gravity, then all we need to do is use gravity to empty the bin and simply meter the rate at which material comes out. And this is what led the team to the Kamengo Feeder. To learn more about why bins plug and the theory that underpins good bin and feeder design, visit the Kamengo website and download our white paper.